Continuing on with our introduction to chromatography, we're going to be talking about separation and column resolution based on the number of equilibria that a mixture will undergo. When we were talking in our last video, we had been talking about relative retention, alpha, in terms of the bigger the difference between two partition ratios, the better the separation. If compounds have a large difference in partition ratios, then they will be easily separated with a minimum of number of equilibria. But if you have two compounds that have very similar partition ratios, very similar affinities for the stationary phase, it's going to take a lot of equilibria to separate them. Therefore, resolution, or ability to separate things, is dependent upon a ratio of their partition ratios, and we call that alpha, the relative retention. And it is K'2, that's the one that has the larger partition ratio, divided by K'1, so the ratio of those two partition ratios, and it is always greater than 1. The bigger number goes over the littler one. Since the partition ratio is directly dependent upon the adjusted retention time divided by the mobile phase time, the mobile phase time will cancel out, and really alpha can be calculated by simply the ratio of the two adjusted retention times. The bigger alpha is, the bigger the difference between K'2 and K'1, the better the resolution. Therefore, resolution is directly dependent upon alpha. Since we're talking about resolution, we can look at these three chromatograms, each having different amounts of resolution, separation ability. If I asked you to pick which one has the best resolution or the best separation, I'm pretty sure we would all pick the last one. It shows the best separation between the two compounds. If we think about why that is, it's really based on two different factors. Notice that the first chromatogram and the last chromatogram actually have about the same peak widths, but the difference in their retention times are different. So the larger the difference in their retention time, the bigger the resolution. Larger T prime, delta T prime R, the larger the resolution. Between the second and third chromatograms, however, they actually have about the same delta TR, but their widths are significantly different. So resolution is going to be inversely proportional to width. The wider the width, the worse the resolution. Resolution is therefore based on the delta TR and the width, W. We can write that as resolution equals TR2 minus TR1 over the width. Well, really, it's going to have to be an average width. So that would be the average width of the two peaks, which gives us the delta TR over width 2 plus width 1 divided by 2. Sometimes you see it written that way. Either way you write it, it's a fairly easy thing to calculate for a chromatogram. It's also important to realize that the resolution is going to be directly proportional to the number of equilibria, n. If you have a large number of equilibria, then the resolution is going to be bigger, better separation. As seen on the SEP funnels, the more the number of equilibria, the greater the separation becomes. So resolution observed on a chromatogram is directly proportional to n, the number of equilibria that have gone on. Since the resolution is proportional to the time divided by W, that's going to be directly proportional to n, we can actually discuss the number of equilibria that must have existed in order to create that particular peak. Remember that the peak is a function of the resolution, the width and the time is resolution, and that's directly dependent upon n, the number of equilibria. Sometimes measuring the width of a peak is hard, but we can do it statistically because we already know that in a Gaussian distribution, most of the peak is occupied in 4 sigmas. This means that we can write this equation, n is equal to T prime r over 1/4 sigma squared, or 4 T prime r over W squared, or 16 T prime r over W squared. The number of equilibria is going to be based on the width of the peak and its adjusted retention time. We can calculate how many equilibria must have occurred if we have T prime r and W. This still leaves us with the problem of how do you measure W? Where does the peak actually start and where does it tail off? And that's sometimes a very difficult thing to measure. So to avoid that, we use a statistical trick which says that the width of the peak at half height, so this is the height of the peak. If we go to half height, we can measure absolutely the time that the width is wide at its half height. N can therefore be calculated as a fraction of that 16, about 1/3 of it at half height. Numerically, it works out to be 5.54 T prime r over the width at half height squared. This is the equation that we use to calculate the number of equilibria. On this chromatogram, all right, on this chromatogram, if we wanted to calculate how many equilibria have occurred, all we'd have to know is this number this number. If we have the adjusted retention time and the width at half height, we can calculate the number of equilibria. The number of equilibria is dependent upon the length of the column divided by how long an area each equilibria is occurring over. This can give rise to the relationship that the resolution is directly proportional to the length of the column. The longer the column, the more the number of equilibria that you undergo. So the longer the column, the better the separation between the two compounds. If the resolution of a column is 1.24 on a 122 centimeter column, how long would the column have to be in order to achieve a resolution of 1.5? This goes back to the square root of the factor of the length is equal to the factor of the resolution. The factor that the resolution needs to improve by is 1.50 divided by 1.24, which means we want to improve the resolution by a factor of about 1.2. If we square that, 1.46. I'm sorry. The length of the column that we want to achieve compared to the length of the column of 122 the length is going to be 179 centimeters long. So if we increase the length of the column from 122 centimeters to 179 centimeters, we will improve the resolution by a factor of 1.2, which will bring us to a resolution of 1.50.